Last time we did set up a very basic render path with a color attachment targeting the swap chain image, right? And even managed to clear that image with some color. But if we run our program, we still have our console output full of validation errors. And the most prevalent one, and actually the only one so far, is about this image layout thing. So I touched this in the last video briefly, that the images can be laid out in the GPU memory in different ways. And this is needed for the GPU to work efficiently with those images. And different operations like reading, writing, or copying or presenting require different layouts to work correctly. So we already see one example of this, that we are trying to present a swap chain image that is in the undefined layout, but we actually need it to be in the present source layout. So that's that. We never specify any layouts for our swap chain images, and there are no implicit layouts, so technically our images are not even suitable for presenting. And the fact that we see at least something is really a pure luck. But what exactly does it mean for an image to be in different layouts? Well, it's up to the GPU vendor and the driver. We only have a bunch of enum values that we can rely on to make the driver hopefully do the right thing. So with that in mind, how do we change the image layout? Well, first of all, the correct term for this is transition. So we transition images from one layout to another. And to be precise, we actually transition not the whole image, but rather its subresource. The same one that we specify here for the image view creation. So like a particular aspect or a slice of layers or MIP levels. This can be in some layout at some specific moment. So how do we issue those transitions? Well, we do this during our command recording with a pipeline barrier command. And what is pipeline barrier? Let me repeat that GPU try to do as much work in parallel as possible. And we already had to deal with this using these semaphores and fences to set up the correct order of operations, right? But it is also important to synchronize work between submitted commands. You see, the spec guarantees that the submitted commands will start in the order they are submitted. But then they will be executed in parallel, and there's no guarantee whatsoever in which order they will actually complete, unless you insert explicit barriers between them. So we can easily imagine it being a problem if some commands write some data, and the next command reads the same data, expecting that the previous write is complete. So without synchronization, it might totally happen that the write hasn't finished yet before we try to read it. So the data will be incomplete or just plain garbage, and, well, bad things will happen. So the so-called pipeline barriers allow us to define dependencies between commands and make the commands after the barrier wait for the commands before the barrier. And we can do it in a very precise manner. We can specify exactly for which kind of access to which exact resource and at which pipeline stage the wait should happen. So sounds good, right? But what does it have to do with the image layout transitions? Well, as it turns out, this is how we do them as well. After all, it's all about the GPU memory being available in the correct state before accessing it, right? So let's take a look at the relevant API. So there is this CMD pipeline barrier procedure, as well as the CMD pipeline barrier 2. Now, one might raise an eyebrow looking at this naming convention when learning the Vulkan API. But you should know that it's also quite common here. Because we all know how difficult it is to design a good API at the first try. It doesn't really matter how professional you are or how hard you try, and Vulkan API is no different. Sometimes the original API is good, but it's missing some features that come up later, or it's not extensible enough, or just plain awkward and someone comes up with a better API for the same thing. So this is why newer Vulkan versions and different extensions often introduce this number 2 versions of the same functions. And I guess we can assume that at some point when Vulkan 2.0 will be released, all this will be cleaned up. But honestly, I wouldn't keep my hopes high because backward compatibility is a very important thing after all. And arguably it's even more important than clarity. Anyway, personally, I think in this case, CMD pipeline barrier 2 is indeed more straightforward to understand and use, so we are gonna use that. But to do that, we should actually enable it. So just like dynamic rendering, this API was an extension before. And indeed, you can still find the KHR postfixed version in the API. And just like the dynamic rendering, this API is now part of the Vulkan core, but we still need to enable it as a device feature. So let's quickly do that. So here in our Vulkan 1.3 features, there is a feature called synchronization 2. Pretty straightforward, right? So if we take a look at the functionality provided by this feature, you can actually also see that there is a qsubmit2 command, which we could also use instead of the qsubmit. But we can actually mix those, and I think qsubmit is simpler to use, to be honest. And it's sufficient for what we want to do here so far. Now let's take a look at the signature here. We pass the command buffer to record this command into, and then this dependency info structure, like this, right? So let's take a look at this structure. And we can already see that there are 3 different types of barriers here. Just memory barrier, buffer memory barrier, and image memory barrier. And this memory barrier is the simplest one. It doesn't distinguish specific resources, but rather defines a global memory barrier affecting any memory access. This is not precise enough, since it's not specific to images, and it won't allow us to do the layout transition, but it's still worth looking into. So this kind of barrier structure defines 4 fields: source, stage, and access masks, and destination, stage, and access masks. Sounds quite intimidating, right? But in reality it's not that bad. It's just a way to specify exactly which kind of access at which pipeline stage must be finished before which other kind of access at which other pipeline stage. This means that you don't necessarily make all commands after the barrier wait for completion of all commands before the barrier, but rather you specify exactly which kind of memory access should happen before some other access. And the driver will guarantee this dependency while still being able to parallelize execution of unrelated commands if possible. Like, imagine you have a compute shader that writes data into some storage buffer, and then you have a fragment shader that reads from it. You definitely want writes in the compute stage to be done before reads in the fragment shader stage. But everything else, you don't really care, right? So you specify this precisely. So the GPU knows it can, for example, already run your vertex shader in parallel with your compute shader, because you'll only need the data later in the fragment shader. Makes sense, right? So the access flux, you can see it's just like read, index read, vertex attribute read, or just memory read, and then you have writes as well. So this is basically different kinds of memory reads and writes. And the pipeline stage flux, well, those are our pipeline stage, right? For the source, you can specify which actions at which stages should definitely happen before the destination actions, or rather accesses, on specified destination stages. So hopefully that makes some sense. Now let's take a look at the image memory barrier, since after all, this is what we're after. See, it also contains the source and destination masks, but also old and new layout. And this is how we transition between the layouts. And obviously you also specify the image in question, and as I mentioned before, not just the image, but precisely the sub-resources that we want to transition. Because technically, different sub-resources in the same image can be in different layouts at the same time. And finally, there's also this source and destination queue family indices. And this is about transferring ownership of an image between different queue families, which is of course a more advanced topic that we won't touch right now, since anyway we are using a single queue for everything. So with that knowledge, let's see where we want to have our image barriers. So we start our frame with acquiring the next image to draw into, the swap chain image, right? Then we begin the render pass, and we use that image as a color attachment. We even specify that this image is in the color attachment optimal layout. And it's actually never in this layout because we never transition it. So here, before this happens, we should definitely add a transition into this color attachment optimal layout. So let's add a to-do here, transition into color attachment optimal. So then we do a render pass, begin rendering, then we imagine that we are drawing some stuff, and then we end the rendering, right? For all these commands, the image will be used as a color attachment, and it is of course expected to be in this optimal layout, right? And after the render pass is done, we don't do any more render passes, and we don't do anything else at all. But you see, after the work is submitted, we are of course presenting our swap chain image. For the presentation, the image is supposed to be in this present source KHR layout, right? So it's a source for presenting. This means that after our render pass, the last thing that we need to do here is transition our image into the presenting layout. So basically we need two image layout transitions, and hence we need two pipeline barriers. So let's start with the first one. So we are gonna create an image memory barrier and specify only this single barrier in our dependency infrastructure, right? Something like this. We create a structure with a fitting name, transition to color attachment barrier, right? Then we can specify it as a single array element, kind of, right, with the image barrier count 1 and the pointer to the structure itself as a pointer to the single element array. So that should work. So let's fill the fields for this barrier out. Let's just start with the image and the sub-resource range, just to bring it in the context that we are working with the swap chain image. So this is our swap chain image, indexed by the image index that we get from the acquire next image KHR. And the sub-resource range that only makes sense here, the color aspect, and one and only MIP level and layer. So far so good. Now let's specify old and new layout. So for the old layout, we can simply specify undefined, because first, it's actual layout of swap chain images right after creation, and secondly, we don't really care which layout it was, and this is also what undefined means in this context. And also, it's important to know that undefined means that the whatever content the image has may be discarded, and we cannot rely that any of the existing content in this image will be preserved, which is totally fine for our case because we have just acquired this image for rendering completely new frame, so we don't care about its contents. For the new layout, it is of course color attachment optimal, because this is what we specify and use when we are using this image as a color attachment for our render pass. Now this source and destination Q family indices is something that we are ignoring, but with this source stage and access masks, it is actually pretty tricky in this case. So the image layout transition is actually a write operation. It might not be obvious, but if you think about this, like if you have an image in one layout and then you transition it to another layout that needs some changes in the data, right? So this is a write operation. And you would think that is okay, and we don't really need to specify any stage and access masks for the stuff that should happen before, because this pipeline barrier is the very first thing that we record in the command buffer, right? We have the begin command buffer and then the pipeline barrier too. However, this image is also being read by the presentation engine when we are presenting, right? And this acquire semaphore here in the acquire next image, as we discussed last time, will be signaled when the image is fully ready, right? And if we take a look at the QSubmit, we wait for this semaphore, right? But we do only wait for it at the color attachment output stage. So, at least as I understand it, theoretically it might happen that the commands that do stuff before this stage can already start executing, right? Like vertex processing and whatnot. And now the first command that we have in the buffer is our pipeline barrier, right? And it will not wait for anything, right? Because we specify empty stage and access masks. So what might happen is that the GPU will try executing the pipeline barrier too, while the image is still being read by the presentation engine, and that's obviously not good. In practice, I never really have seen that happen, but the validation actually catches this case and complains. So what can we do about this? Well, one solution that is not very nice actually is change this pipeline stage flags for waiting the acquire semaphore to something like all commands, which is a kind of meta pipeline stage that basically includes every command that can be executed. So the semaphore will be waited before doing anything at all. Now, this is not ideal, because if we are not touching the image, it would be nice to do some unrelated work. So this means that maybe we can scope this to this specific barrier. And what we can do is specify the all commands bit here for the image barrier to make sure that all the commands at all, apparently including the presentation engine reads, will happen before this barrier. And also we can specify the access as memory read, right? So this means that this memory barrier will be applied to all the reads for this image by any command at all. That would include the presentation. So I think this is a good enough solution. Maybe there is a better one, I'm not sure yet, but we will roll with this for now. Now we need to specify the destination stage and access, so what exactly will be blocked by this memory barrier. And since this is about transitioning the swap chain image into the color attachment layout for using as a color attachment, the destination stage is logically the color attachment output, right? And the destination access is color attachment write. So let's reiterate a bit. We insert the pipeline barrier that contains one image memory barrier for our swap chain image that will ensure that all the memory reads for all the possible commands for all the possible stages will definitely happen before we get to the color attachment writes in the color attachment output stage. And since there's a layout transition, when we get to the color attachment write, the image is guaranteed to be in the color attachment optimal layout, which is exactly what we want, right? So this barrier is done. Let's go to the next one. Here it is. And what do we want to do here? Well, basically we want to say that after rendering, so after the color attachment output, we want to transition our image from the color attachment optimal layout into the present source layout. Let's start filling out the image memory barrier here. So we define a new image memory barrier 2, transition to present source barrier, right? We add it to the dependency info, just like the previous one. Single image memory barrier, right? Now the image is of course the same swap chain image. The sub-resource range is the same one. Now the old layout here needs to be exactly the expected layout of the image, which is color attachment optimal, right? If we specify and define here, then it's not guaranteed that the contents will be preserved. However, of course, we want the rendered contents to be preserved for presenting, right? And the new layout is of course present source. Now, what should happen before this pipeline barrier? Well, as we said, we want the transition to happen after all the colors are written. So this would be color attachment output stage and the color attachment write access. Make sense? And for the destination, I think we don't need to specify anything here because, well, this is the last thing we do in the command buffer, so nothing really should be blocked by our barrier. Hopefully that makes sense. And by the way, in Odin, we specify an empty bit mask. However, in C API, this is often mentioned as pipeline stage none, which is basically 0, which is what empty bit mask in Odin is, right? And it's the same for the access flags, there's this none constant. So now if we run our program, we see no warnings at all, right? We do see some validation errors when we close the program though, and we'll get to it in a bit. But before that, I wanted to mention an important validation layer setting that you can use for debugging any synchronization issues. And this is this synchronization validation area, right? If you choose here the synchronization preset, that will enable it. Now, if we run our program, we will still see no errors, which means that hopefully our synchronization is fully correct. Now, before we wrap up, let's actually take a look at these errors that happen when we close the application. So this is basically about destroying the command pools and the semaphores and whatnot that we do here, right? We use defer, so it will be called in the reverse order after our main function exits, right? So basically here, after we exit our main loop. But the thing is, remember, all the GPU interaction is fully asynchronous. So what might happen is that the CPU will stop the main loop and then all the deferred destruction will be executed, but GPU might still be using all these resources. So the easiest solution for that is here, after we exit the main loop, we can insert this device wait idle call that takes a device, and what it will do is just block the CPU until the GPU is fully idle, which sounds good enough for the shutdown. Let's wrap it in VK-check, run the application, close it, and see that we only have 2 errors. And those are about the semaphore and the fence that we simply forgot to destroy. And this would be these ones, right? The frame fence and the acquire semaphore. So let's quickly add deferred destruction. Like this for the semaphore, and like this for the fence. Let's run it again. No errors. Let's close. No errors. Finally. So figuring out memory barriers is actually a huge deal, and this is something that you definitely want to get right if you wanna seriously use Vulkan. So maybe it makes sense to meditate on it, and I'm sure we'll be using memory barriers even more in future, so it's not over by any means. But I just hope this video was helpful. So stay tuned for the next one.